Hello everyone, thank you for coming. We are going to start our second Engineering Graduate Research Conference, and we are pleased and honored to have this event in person after lots of looking at the screens and at home, being at home and being away from the community that we have in the college. We are really happy to have you here in person, seeing you face to face. So thanks for coming and thanks for giving us that opportunity. So first of all, I want to welcome Constance, our Associate Dean of College, to give that first welcoming message to graduate students so that we officially start our second Engineering Graduate Research Conference. Thank you.
Can I introduce Jim Boire here? Well, yeah, welcome back to the building. I know this is probably not new for many of you as it was for the faculty, because we wouldn't let the faculty in, but we tried really hard to let you in. So in March, when we had to leave, I'm actually quite proud to tell you that the College of Engineering was the first people out, but we were also the first people back in our labs on campus. So there was a lot of other colleges, including medicine and others, that were not in their labs when you guys could get in. And so I also want to personally thank everyone for your cooperation. I know it was a bit of a hassle. We divided, as you know, we divided the building into 6 zones, and we had 6 different entrances, 6 sets of washrooms, but it worked. We didn't have any incidents in our building. There was Med had a case, CLS had issues, but we didn't. And so I'm really thankful for the cooperation from you as grad students and also our technicians. So again, thank you and welcome back to the building. Jim Boire is a homegrown Saskatoon fella, and he first of all went in and went to what would have been Kelsey back then, I suspect. Got his machining ticket in about 1990. Was a machinist for a number of years and decided to come back and get his engineering degree. Graduated in 1996 with his mechanical engineering degree and started RMD Engineering, which is a machining industrial automation type company. He's grown that company, and when COVID hit, Jim and his company decided they wanted to do the right thing, and they actually undertook to develop a COVID emergency ventilator system, a unit. And we're successful at it, and you may have heard in the news, this is where you heard RMD Engineering, is that they received Health Canada approval for that instrument, and are now actually expanding, I think, your company into some of that healthcare manufacturing type stuff. And so anyway, welcome Jim, one of our alumnus, which is actually living up to that, be the engineer the world needs. So thank you, and welcome everybody. So
thank you so much.
All right, well, this is it's going to be a little interesting. Going in here, we'll start this. I'm going to run kind of with both. So my notes are down here, and as a good engineer, I finished this up at about 5 o'clock this morning, and went out of here once with my wife. You guys, how many undergrads are here? Thank you for coming. There's job applications at the time. And we ran through it, and it was good. So thanks for the invitation to come and speak today. I had a lot of fun getting ready for this. And the name of that presentation changed a number of times when I was thinking what to call it. So what you're going to get is an unregrettable recollection of the sweet and sour of 25 years of trying to get this right. You never will get it right. If you get it right, it's time to retire, because you're not trying hard enough to break stuff. Because there's a bunch of engineers in here, I don't know if you've seen in my notes up here, we're going to recite the engineer's prayer. Anybody know that? No? Okay, you have to say it with me. I'm an engineer. I can change. If I have to. I guess. Okay. Now, obviously, I stole red from red green, but looking out here, I don't know if anybody other than Terry would know who red green. So we're going to go through the agenda here really quick. It's going to be about 25, 30 minutes, depending on how fast I talk, or if I get too close, I can't read. If I get too far away, I can't read. If I have to scroll down and go to the next screen, it's just going to delay everything. So we're going to have a brief background about myself. Why do people choose to go into grad studies? And why I chose a bit of a different path. Why multidiscipline approach has worked for me with some examples of our projects, and how that led to the ability for our company to build an emergency use ventilator during COVID. Then I'm going to talk a little bit more about some different reasons you might want to do grad studies, and I'm going to give you my opinion of when you should do grad studies. So we'll get into that. First of all, I'm a machinist, and anybody that doesn't know what a machinist is, do not go watch this movie with Chris. Don't do it. He's a bad man in that movie. And that's not general of all machinists. Quit looking it up. I see that's what you're doing on your phone right now. As a machinist, I went through and got my Red Seal German ticket. And when I graduated from high school, I knew there was no way I was ready to go into engineering or something that required me to sit down for more than 15 minutes at a time. So I did go to, it was called Kelsey at the time, but SciAst, and now it's called SAS Polytechnique. And then I worked in 3 different shops over the years, gaining experience in a lot of field work, CNC programming, and ultimately in tool and die making. And that'll come clear why that was important for me later. On the right up here, you can see that's an injection mold. I think that one's to make little floating balls that are in test tubes for agitating them. So a little bit of history. Like I said, after I had my ticket, I started upgrading some of my classes. And then in 1992, September 1992, I started at the UofS. Who was born before 1992? Oh, that's better than I thought most of the graduate students. Back then, they called us mature students. If anybody seen the way we behaved after, that was not the right term. I took the liberty of downloading this from the website, updating it for some relevant information, and it should be available on Wikipedia now. The key dates to look at is 1965, 68, and 1996. Dean Nikiforuk, I don't know if anybody remembers him. That man was a legend, and he waited until I graduated to retire. Not really. He hired me and then left.
So my CV, when you finish undergrad and you start working as a graduate student, it's no longer called a resume, it's called the CV, which stands for curriculum vitae. All I did was pulled out the 3 main places that I worked. So I instantly graduated, started working as a manufacturing engineer at Standard Machine here in Saskatoon. Fantastic shop, started by a fellow named Gary Porter back in the 60s, out of his back garage. Barb, his wife, who's a fantastic lady, kicked him out of there, and then they started that, and now Timken owns it. They are one of the largest machine shops in Canada, and definitely one of the largest gear manufacturers. If you ever get the opportunity to go see that company, fantastic. Moved from manufacturing into potash, and given the 20th anniversary of the terrorist attacks in New York, I knew exactly where I was when those planes hit that tower. I was in the control room working as a maintenance engineer and a dry process supervisor in the plant at the time, and that took your breath away. It's crazy that that's 20 years ago now, but that's where it was. I then moved to SAS Power, and I had a really cool job. I worked out of operations support, and as a machinist, they sent me around to all the mechanical plants, so all the coal-fired power plants, and I got to go take a look at what they were doing and see what we could do for opportunities. And basically, it was the beginning of learning process. And for us, and we'll touch on this a little bit later, process is really what drives
anything that you're trying to learn. So if you're trying to figure something out, you need to know what the process is. If you're learning something and studying for a class, if you figure out the right steps in the way your brain works, you've figured out a process. That's the same thing with that is a common theme in all of those. So, what the heck are you thinking? Grad studies, why do you do it? This is a little bit of an interactive part. So who are the grad students here? A lot of grad students. So far back corner, why did you go into grad studies?
It was a dream of mine, like since I was years old. I saw my parents studying.
Okay. Who else?
I just finished undergrad. I sat down with an engineer from a consulting company, asked him how many of your employees have a graduate level education, and he said about half.
Yeah.
And at that point, I realized, oh boy, I better get in for grad studies.
Okay. Seema, I know you're not
I'm
in
not.
graduate studies.
No, I'm not. I am an old graduate. Yeah. And, you know, I love studying, and it's that only reason that I continue.
Yeah.
Yeah.
Is there any foreign students here that came and need to do graduate studies as an equivalent for your PEng? No? That's new. I sat on the experience review committee with Apex for a number of years, and that is by far one of the easiest paths for people to get their PEng in Canada, is to come and do postgraduate work. So there's a number of reasons why people go into grad studies, and some of you know, or we've inferred upon it. I'm currently registered as a PhD candidate in biomedical engineering, and when we finish up the presentation, I'll let you know why I thought this was an important next step for me. So, no one really chooses the path of most resistance. However, as it's turned out for RMD, it's by far the most interesting path we could have gone down. Obviously, a labyrinth like this does not grow in Saskatchewan. We have cornfields. Anybody ever see any of our cornfields and our mazes? That's what we have here. I thought this was an interesting perspective on how to interpret what our company has done for its path. Most, if not all, of my team has attention deficit disorder. I'm not saying that as a derogatory term. I'm saying that as a reality. Probably back when I was growing up, if they had Ritalin at the time, they would have tried imposing that on me. We've all come to appreciate what that can give us, though, and the type of people we have to work with in order to keep that kind of in check. And in order to be successful. I love the stairs in this because that maze is really, we are those people that run around in a maze giggling. We like the puzzles, we like the different paths that we can take. And the stairs are kind of cool in this one because it's kind of where we get out of that fray. You get out of it, and every so often you can take a big look and see where you came from in order to go. So now that we've learned all of this, where do we go next? So I wanted to show you where we came from and the types of projects we started with. So we need to start at the beginning, and I would like to say that it started with a big bang. I thought it'd be better. I did a presentation for Apex, and it was remote, and I had so many good one-liners in there, and it was crickets. It really, really kills me when you think you're funny and nobody else responds. Not even a clap. But it didn't. It started with a universal joint, a big universal joint. So, who's from Regina here? Anyone? Yeah, I wouldn't put your hands up on it. Every good Saskatoonian will obviously note that that's a Regina phone number on there. I started RMD in 2001 and worked on it in the evenings while I was still working for Power and Potash. Doing drawings, design work, and I always had a little machine shop in my garage, always making injection molds and everything. I came up with this idea when working in Potash And it was a good idea. This is a 350 horsepower universal joint that runs at about 12 RPM, so you can figure out the torque, it's huge. And they still use it right now. However, in 2003, there was a failure on a big universal joint. If you can make this one, how come you can't make it bigger? It was a failure, and it ended up on the floor. Fortunately, because I worked in potash, it was one of those things where I took the phone call and they said, "Hi, yeah, do you want to come pick up your junk?" And I hopped in a truck and did the walk of shame down the aisle, went and looked at all the pieces on the floor and took it back. But because I had worked in process, and specifically in the dry process area, it was determined very quickly, because I knew how to do all of the logging and all of the looking at all of the graphs that all of the operators run, it became very quickly apparent that the process was screwed up. And when we finally said, we need to come out and take a look at what's going on, they said, well, the machine is shut down, but you can look at some other stuff around there, but we've got it red taped off. When we went out and looked at why it was red taped off, the whole floor was vibrating so bad, you couldn't walk on the floor. So we went and looked at it, and 3 of their 4 compactors, these run a compactor, which takes powder and squeezes it into pellets, then they crush it up to make granular product. 3 or 4 of them had a feed tongue that diverted the potash evenly across the face, and they weren't maintained, they weren't broken, but you could see all of that in the trends on the computer screen. So at the end of the day, we showed them where the problem was in the process, and thank God, because I don't know any new graduate engineers that get out of school realize you don't make any money for the first 4 or 5 years. I had no way of paying for new ones for them, and at the time they didn't want it back. So made the decision to move back home, rent a 1,200 square foot space, and start making this stuff myself. So moved back to Saskatoon in 2003, and anybody that takes a look at our coffee mugs, it said we had a 15 or 10-year anniversary in 2013. I did that because that's really when I felt RMD started, was when we started manufacturing stuff. So when we moved up there, there was 3 of us, and we started with what I knew. Potash and mold making, and almost instantly grew out of that 1,200 square feet and moved into a 6,000 square foot facility where we expanded to start doing all types of welding. So pressure welding, CWB welding, a lot of TIG welding. And then we added finite element analysis capability. And we quickly became known as this group of wackadoodles that would try anything. Safely, but we would try anything and come up with different ways of doing it. So that is hard to see, but that thing has to be supported by a semi, and then it sits on that big boring mill that is about 14 feet tall, and that hole is about 12 inches big. And we had to rebuild that thing. So that, I call it a small segment, is from an O&K shovel used at one of the uranium mines for open pit mining. So this is what dug up all the rock. They blast it, it falls down, they dig it up, and they put it out to be processed in the mill. So as it turns out, the pit that shovel came out of has now become the mine's tailing facility, and tailings facilities are just where they dump all of their waste process material. And we are currently designing and building a barge, and we went out and tested it this weekend, to go back up to that tailings facility now and install some subaqueous lines for fixing their deposition rates. It's a pretty cool project. It includes 3D underwater mapping, and the coolest thing is this has to be done in 6 weeks because it's going to freeze. Water gets stiff up north. I don't know. Who's not been here for a winter? It's going to get hard. Don't go swimming. So that's some testing we actually did this weekend. And actually the best part of this project, Amanda and I went around for a little nostalgia tour here after lunch, and I started laughing when I got to my graduation picture. But the cool part about this project is I got reunited with a really good friend. I'll offend somebody right now. Unfortunately, he went into civil engineering. I know. But he graduated in 1996 as well, and now he's the vice president of environment up at Orano. And he wanted to work with us on this project because, again, not a lot of people wanted to take this on, and for us, it's kind of a fun one. So we're going to go back in history. So back in the early days when we started doing controls and automation, again, because we started building stuff and could do innovation to implementation, so you come up with an idea, you go up, talk to all of the process people, talk to the millwrights, talk to the operators of the mills and the mines, and you go up and you ask them what their problem is and what do they think you need to fix it. We got involved with some big projects really quick. So everything from building a uranium packaging system that the CNSC had shut down Cameco, and they needed to put that in, to stuff like this, which is an automatic metal removal system. So when you pick up all that ore from the mine and you dump it in there, you're never going to believe it, but you find metal bits from the backhoes and you find metal bits from the truck, helmets, everything. We find everything in there. And what you see at the bottom of this screen down here is what's called a ball mill. So all of that material comes up, goes through this magnet and material removal system, and then into a ball mill to turn it into a slurry. But if you start pumping metal into there, it's just going to shred that ball mill. And inside that ball mill, because it's a uranium mine, you can be in there working for about 3 minutes before you exceed your daily dose. And if you're coming to the end of the project, you can be in there for about 10 minutes and then you're done for the year in there. So you try and make their processes as safe as possible outside and process things elsewhere. Then we started working with the Canadian Light Source just about from day one. We've been very fortunate to be in there for now just about 20 years. One of our largest collections of automated equipment that we've built is located in the biomedical imaging line. I don't know if anybody's had the opportunity to go through there. It is one cool place. It's a multi-billion-dollar facility. And this is where I met a man named Dean Chapman and his team. And we spent years working with their physicists, engineers, instrumentation people, learning about what that thing does. For a mechanical engineer, that is just about as mystic as electrical engineering or physics. We don't go there. Well, we do, but I don't. In the picture here, you're going to see this large animal positioning system right here. So that's about 5 meters in diameter, and it goes into a 5-meter pit. And that was originally intended to image horses, large animals. And then in the back is a pretty cool detection system. So the way imaging works is you take this beautiful beam of light, filter it, shove it through an object, and then you have a detector to pick up what's left. And then from what's left, you can work backwards to see what you just went through. So nothing was ever built on this scale before. So we built this. And if you notice the clearance on the roof, when I was going through this, I was just like looking at the pictures going, what were we thinking? Because we got to get really creative. We had to close the doors, lock them, put some paper over the windows so nobody could see what we were doing. We were safe, but to people looking on, it wouldn't have been so safe. And then right through to collaborating with a company called Huber out of Germany. And this is a canine prostate system for holding canines, because as it turns out, canines get prostate cancer just like human beings. So they use that to image. So we have to worry about what kind of materials we're using and everything, and fairly cool. That led us into, they had problems getting crystals, and when they were commissioning the beam line, the first thing they did was run one of the beam splitters through one of the crystals and broke it. And those are usually 16, 20 weeks away. So we got our chance to start cutting crystals, orienting them, cutting them. So we started manufacturing them. And then Dean and his team had this brilliant idea to start bending crystals to get different attributes out of them. And silicon crystal is literally that silicon. So it's hard as glass when you bend it. it usually wants to break. So we got a lot of experience with that, and now we build these at our company. And it's finicky stuff, high tolerance, but fun stuff, very rewarding to see images pop up during this, which then led us to building, this was a cool project, the world's largest elliptically polarized undulator. And when we started that, it was like every other project. Everybody in the shop went, huh? But it was cool in the opposite sense of that term, in that because it's a bimetallic construction, everything had to be at the same temperature when you machine it. Because when you put it in the light source, they hold that facility at 24 degrees, plus or minus 1 degree Celsius, and in actuality, it's less than that. So we had to have our entire shop at 24 degrees, plus or minus 1 degree for an entire year. Awesome in the winter, not so fun in the summer, unless it got to 40 degrees outside. Then it was actually a good place to be. So it took us a year to make that, and it was right when we moved from our office in Saskatoon. We built a new facility. That 6,000 square foot facility we had turned into a 20,000 square foot. We were always expanding, always adding on to it. And then when we built this, we were like, there's no way we can build that in that facility. So we built our new 60,000 square foot facility, thinking, how could you ever grow out of 60,000 square feet? We did. But that was built out there. The interesting part about this project is it took us a year to make it. It took the physicists a year to put, I think there's 24 or 2,600 rare earth magnets in there. And it took them a year to put them all in and map that magnetic field. So it was crazy. But this is a good example where we had all of their people working with all of our people. And it was a fun collaborative thing. And this is where we quickly realized these big projects need project management. And I think you see that now in your engineering. You start taking project management philosophy and stuff. Whatever you do, don't call yourself a project manager and say, I've worked as a project manager. I was the project manager on my team. You'll annoy people that actually do that for a living because it's another designation. It is. So we all went and got our PMPs. We wrote the tests and got our PMPs. It took 4 years. It's just like your degree. But they take it seriously, and it is a full-time occupation. So if you ever get the opportunity to do that, that would be great. So that, however, didn't give us our first 15 minutes of fame. Our first 15 minutes of fame was a cow tipper. For those of you who are not from the prairies, cow tipping is this fictitious task of going into the field at night. There might be wobbly pops. Does everybody know what a wobbly pop is? No? It's probably best if you don't. It's beer. In my age, it was stubby beer bottle. But, so you go out and you try and push over a sleeping cow. So 2 things. Cows don't sleep. They lay down to sleep. If they're standing, they're very much awake and waiting for some inebriated ag or engineering student to come out and try and tip them over. If you think you succeeded, probably what happened is you had one too many wobbly pops and you fell over. Now the cow looks like he's laying down. The best way to check that is look at the stars. If they're straight in front of you, you fell down. It is believable that we could build a cow tipper here in Saskatchewan, and specifically out of this college, because you got engineers, you got ag people, and you've got vet med people, right? You can check. What do they throw now? Nothing, right? Because it's COVID safe. Balloons or red paint or something. So why not? Why not be able to build this? Who would complain? He might. There was hardly any protesting when we did it. And no animals were hurt during these videos. It's crazy. It's crazy what that thing does. Now, we didn't design and build that. And just to reiterate, no animals got hurt during this. It was an utter success. See, I got nothing at AK. Not even a ha-ha. So thank you. Again, job descriptions or applications or just kidding. Okay, you're not vets. Not one of you is a vet. This gets an awe at the vet college when I do this because courts are cute. This is one of those jobs where we will. Oh, sorry, you didn't get to see it either.
There we go.
That's where I said just kidding. So we could try it again.
Aw.
This is one of those jobs we were able to integrate all of the people involved, from the techs to the vets and the finance people, believe it or not. And a lot of our tradespeople that were so interested in salvaging this 40-year-old technology that came from a Saskatchewan engineer that was a vet who came up with that unit here. He did that, that was 40 years old. And they said, no, it's not safe anymore, too wobbly, things don't work, we need to scrap it. So they put out a tender for somebody to come and replace that. But the tenders came in at like $1.5 million or something silly. So we put a proposal in that said, hey, why don't we just update it and fix it? It's still there, the metal is still there. Yeah, some of this other stuff is worn out. So that's what we did. We ended up redoing all of that. And it was a fantastic collaboration between a whole bunch of different places. So, and it also introduced us to a whole new group of people that did research and work in what's called the One Health world. And as most of you know, One Health by definition is the collaborative efforts of multiple disciplines working locally, nationally, and internationally to attain optimal health for people, animals, and the environment. So again, as you get older and as you go through things, certain things become important to you. For us, a lot of, if you ever get a chance to come on a tour of the shop, you'll see we recycle so much equipment, and we like reusing old things. Some of that stuff is built very good. So we took a project that we had started for human health, and it was a rehabilitation project that we did with some MS patients here in Saskatoon, and then partnered up with the Saskatoon Health Authority and collaborated with a lady named Dr. Julie Montgomery, who's at the WCVM. And we designed and built a horse rehabilitation system to try and treat horses that have laminitis. Anybody here have horses? Yeah. Terry, what happens to a horse if it breaks its leg? Yeah, they're euthanized. And it doesn't matter if they break their leg, it might be lameness. And if they start walking funny and their foot starts swelling, that's it, the horse is put down, just because it gets so painful. So this system is now, the system you see up here is real, it's not just a 3D model, and it's currently installed at the WCVM. And Dr. Montgomery's grad student just did her defense on her master's this year, and I think Daniel oversaw that as the grad chair of BioE. So she graduated with a master's in biomedical engineering. The cool thing about that project is it is just the beginning. When you start doing something that nobody else does, you open up doors to everything you look at is just about another research project. So first thing we realized is when you're lifting a 500-kilo horse, they're a living, breathing animal, just like human beings. They get pressure sores. So if anybody knows anybody that's bedridden or sits in a wheelchair all day, one of the biggest comorbidities they get is pressure sores, and those pressure sores can do a lot of damage to them. So if you have to rehabilitate a horse, it's no different than a human being. They have to be weight reduced for 6 weeks. So when you do that and you're holding up something that weighs 500 pounds, we came up with this system, and this is part of Samantha's project, to use multiple airbags. But again, on the first one, you need to go as big as you can. So that system there is the most instrumentation we ever put on one device. And horses don't like it. If you had that many wires hooked up to you, you'd be in some 1980s thriller sci-fi movie, but the horse did not like this at all. So we had to get a little bit more creative. The other thing it did was it pushed us and the research into the synchrotron world, or for me, back into the synchrotron world. where we were able to put together a set of experiments with a group out of Australia where we were able to actually image the lamina. So the lamina is what holds the hoof of the horse onto the bone structure that they actually use to support themselves. And it was readily apparent that what we were looking at far exceeded what we thought it was going to do. So you'll see here that the image on the left is a standard CT image that they do with the highest resolution CT machine that they have in Australia. And on the right is a phase contrast image that was done in the synchrotron by rotating this hoof. And we got to inject it with a contrast agent. And you'll notice all these little tiny spots are just blurred up here. Here they have really good resolution. So the gold standard in a lot of stuff, when you look at it, when you actually get down to the cellular level, is histology. So histology is now just taking that hoof, cutting it into slices, and taking a look at what you see. So this is inside the hoof, and you can see the little pieces where it comes from. So this is what holds the bone, or the toenail, onto the bone structure. And it's all these long fingers, which are called lamella, which you can see in the CT, or in the synchrotron image. And then all these little things are what actually do the grabbing. And they're called secondary lamella. All of the vets that were involved with this project got really excited when we started doing this. Why do you think that is? It's non-invasive. You can imagine, lamella studies have all but stopped now for obvious reasons. It's very painful to the horse. And to get a histological slide, they've only got 4 hooves. So you can only do 4, no, I'm kidding. You can only do 1. So you have to euthanize the horse. So it makes it almost impossible to study. So they were really excited to see this, simply because as a group, they figured out how to do something that's never been done before. So it worked out very well. So we get into some more cool stuff. At the same time, we grew our company in 2014 by adding Scientific Instrumentation and Saskatoon Machine Works to our group of companies. Scientific Instrumentation was this really cool little company that specialized in source level automation. So building from the chip up, which was really cool. So they did all of that, and they also, in collaboration with some technology that was developed here, we built a Canadian advanced digital ionoser. When I take people on a tour, remember I said I don't do physics? I tell them what that machine does is it's what puts the bat signal on for people to see. And then they told me to stop doing that and to take it seriously. But the other thing they do is get into high altitude ballooning because what you're measuring is the ionosode. Now, the balloons don't go up that high, but it does have the ability to go up high enough to start seeing what impact does this have on the ionosphere. So we started doing that, and we started building valves to control the balloons. So unknowing to us, 2 groups used our valves. They bought valves through some third-party company, signed a whole bunch of disclosures because they wouldn't tell us what they were using it for. And 2 groups set high-altitude world parachuting records. So the first one was that crazy bugger that owns Red Bull. His name is Felix Baumgartner, and he went up in a capsule. I don't know if anybody's seen those YouTube videos of him going up in a capsule, and he was scared to death. You could tell. He was just scared, and then he grew some wings and jumped. You didn't think I was going to say wings, did you? And he broke the world record and flew up 127,000 feet. And some people can do the math. It's a long ways. And then in about a year later or 18 months later, a fellow named Alan Eustace, who was a Google exec at the time, said, that's extremely wasteful. I think pushing boundaries and pushing envelopes is fine, but not to excess, because I think Red Bull spent just about $20 million doing that. Alan used a different approach. He strapped his ass to a balloon. Now that balloon Has anybody ever gotten, I know students won't, maybe profs might have gotten dry cleaning done? Yeah, how thin is that bag? Like 2 or 3 mils. It's like you stick your finger through it. That's what these balloons are made out of. So, and when it's up in the upper atmosphere, Alan took a picture from above, he had a camera, and he looked up, and that balloon is now 400 feet in diameter when it gets up there, because the pressure drops and the balloon expands and takes it up. So Alan, just to spite Baumgartner, went up to 135,000 feet, and he says, I'm going, but this is good enough for me. And he discharged, he broke free of that, and then he free fell, and broke every other record that Baumgartner did. So it was kind of interesting. And then, as it turns out, our valve is now in the Smithsonian in Washington. So we got to meet this fellow, that is Sir Julian Knott. He was the one that helped them with all this ballooning stuff, and I got to meet him. And they were doing it around the world flight. If you ever get a chance to look up Julian Knott, amazing story, tragic ending. It was one of those times in your life as an engineer, when you design something and build something, and something horrible goes wrong, you get that pit in your stomach. This was one of it. On March 26th in 2019, I got a text from his wife. We spent a ton of time together, and him and another fellow did a test flight on this, and the winds changed on them, and they came down hard. Everybody was okay. Then he got out of the capsule, and the wind came up and picked up 2 of these 400-foot long balloons and pulled the unit over a cliff. And my silly bugger of a friend here thought he could stop it. And he got tied up in it and went for a tumble and ended up dying. Those are the things you remember. But the pit in my stomach when you heard that he passed away, and you were part of making something, those horrible feelings are what let you know you should still be doing what you're doing, because you're going to second guess everything. So one of the things that we talked about is, why were we able to make a ventilator? So this brings us to what is now probably the best collaborative project that our company has ever been involved with. And in March 2020, we created this volume controlled ventilator in response to the COVID-19 pandemic. The world had made this call for ventilators. There's been a ton of articles written about it, but probably the one that's best describes the collaborative effort was written by the College of Engineering's Lamella, and I never planned for her to be here. She's here. Read that article. It's so well written, and it's about me, so I'm biased. But mostly it's about how we did that and the collaboration, and it's a pretty cool story. So the Coles Notes is, we're going to look at the timeline next, but the Coles Notes is my daughter, who is an ICU nurse and currently doing her PhD in nursing, sent an email to us and said, this is worse than anybody's ever seen. Our ICUs are full already before these people come here. It's going to get bad. We don't have ventilators. We don't have this. Stay home. Stop the curve. And of course, being engineers, we never listened to any of that. We just said, there's a fire. What can we do to put it out? And so we started building this ventilator. Please take the time, if you have not read the Noah's article, read it. It's, engineers are not supposed to be proud, and if you ever come work for me and you get proud and you start bragging to people, I will pound it. It's very tough being up here bragging your company up. This, though, isn't just my company. This was Dean Cresta. This was these people down here that let us come to this building and steal lathes out of central shops at, I don't know, 2 or 3 in the afternoon and take them away on a truck. It was very cool. So a bit of the timeline. So Becca texted me on the 17th of March. which I don't know what that was, a Wednesday night, and as a good father, I looked at the text maybe the next day, so it was Thursday. And that's when we went, okay, well, what do we do? Let's get some stuff into place. And by the way, I think we can build this. Why would you think somebody would be so arrogant to say, I can build that? And it's probably because you work with a fantastic group of people. So again, this is just a basic outline. The timeline has the two sections, like I said. That little circle on the left, that is Friday night, Saturday, and I think I called Suzanne on Sunday night and asked her to come see us. So we're going to touch base on something called MedHack next, and some of you might have got that invite. This is basically what that was. We had 20 people in a room, and it was mayhem, trying to figure out what we can do, how we could do it, what codes and standards are needed, how does this work. And we built our first prototype in 2 days and had it up and running. Now it was computer programmers and everything. It was like a military exercise. Just organized chaos. So we did that, and the reason I asked Suzanne to come see us, first thing out of her mouth was, well, no, I'll send Daniel. You guys would know him as Dr. Chen. And I said, well, that'd be awesome, and it'd be great, but that's not what we need. We're pretty confident what we made. We have no credibility. None. Zero. We need you to talk to the Dean of the College of Medicine and tell him that we've followed a process, and let us talk to them to make sure that we do the right thing here, because everybody there was flat out getting ready for a pandemic. You didn't want to waste their time. So that's why she came, took a look at our process, took a look at everything, and then on the way home, she had Preston Smith, who's the Dean of the College of Medicine, on the phone saying, this is real, it looks good, you need to get somebody out here. So we're very unique in Saskatchewan, and definitely in Saskatoon with the University of Saskatchewan here, because the healthcare system is kind of parallel run between the government and the university. So we were very fortunate to get a fellow named Mateen Razi, who is the province's head respirologist, on board with us. And he came out and vetted to see if this was actually going to do what it was supposed to do. And this is where we said, now the big circle starts, because I think it was, I don't know, March 25th or 26th or something, he came out and he said, yep, I do believe that this is what's going to go. And he went to the province and told them, yep, this is what we should be backing for Saskatchewan's. If Saskatchewan is going to put their hat in the ring, this is what we should be backing. So what we did was, if you count this up, I think it's 42 days from the time we actually went, okay, go, to when we submitted everything to Health Canada. In between that, you can see we had to get Intertech, because you cannot put something down a person's body without having third-party testing on it to make sure everything is safe. We had to make a whole bunch of stuff, because if you remember, there was a bunch of hoarding going on. So we actually made all of our own proportional control solenoids, wound the spools and did everything. And it was about somewhere at the end of this, I think I even put something on here. Yeah, right here. This is with the College of Engineering. To have 6 third-year mechanical engineering students come on board with us. And that was the best time ever. Like, these kids come in, have no idea, we were under a confidentiality clause. And those 6 guys bonded instantly. And they built the room where we did all the testing, they built benches, they made parts. 2 of them ended up staying on after the summer was over and did a full internship with us, and they're just back in school now. And we had such a good experience with that. We hired 5 more engineering co-op students. So they're there now doing similar things, just in 5 different areas. So again, one of the sad things we'll talk about later is we did that in 42 days. And then we submitted it to Health Canada for approval. So while we were waiting for the device to be authorized, we put a lot of our effort into getting our company certified to manufacture medical devices. This is an ISO standard on steroids, and it really has all the components you would want to have in your company, but it is a mountain of paperwork and very labor intensive. We were also really fortunate to have associations with 3 people. One was Dr. Montgomery from the Western College of Vet Med. She was on sabbatical. Patricia Farnese, who was a prof over at the College of Law, she was on sabbatical. And my daughter, who was a nurse doing her PhD. She wasn't on sabbatical, she was doing her PhD, but it's in public health. So all that got put on hold. All their projects got put on hold. And they all instantly got permission to change their sabbatical to helping on this project. Because this is massive. It doesn't matter if you build a ventilator, how are you going to train people to use it? Because you have to have all the training material. And then how are you going to get certified to manufacture it? Because you had to have a quality control program in place. Okay, I'm just, this is like the bell. 1 minute?
It's like 5 to 10 minutes.
Okay,
Exactly.
all right. Does anybody know how to push that 1.5 button on YouTube? I need some Red Bull right now. So we ended up collaborating with them, and it was fantastic because they had, if you ever need to get through 30,000 pages of standards, hire a lawyer. They love that stuff, and they just flew right through it and helped us navigate that. So the long and the short of this is we got our company certified for what's called MDSAP, which is manufacturing capabilities. And in December, on December 30th of 2020, we finally got our approval from Health Canada. It unfortunately took 7 months for them to get to look at it and see what was going on. We're going to skip this slide. I do want to cover off this because this is kind of cool. I said I wasn't going to brag. We're going to skip that. We did lose the race though, and ultimately certified prototype in North America. The guys that did it in 39 days. We did it in 42, and it sucked to hear that because our heads were down in the sand digging and we were going. And so we started asking questions, were they smarter than us? Did they have more resources, more equipment? I said, how the hell does this happen? And then we found out it was NASA's Jet Propulsion Lab, who had an annual budget of $6 billion and nothing to do. So we didn't feel too bad when we found out that they had $6 billion to play with. That's their ventilator on the left. That's our ventilator on the right. So we didn't feel so bad all of a sudden. And then when we went back and looked at it, somebody was even better than that. They built their prototype in 32 days. Now, I really want to try someday to blow 20 million pounds in 34 days, because that's what they did. And that's what theirs looked like. So the interesting part about this is NASA got their ventilator approved in 3 days because the FDA worked with them and they got it approved. They never made one. They said, we're not making it. Now that it's here, everybody else go ahead and make it. But you couldn't do that. You had to be certified. You had to follow a process. Finally, I wanted to show you what Canada's ventilator looked like. This was a 20-year-old design, and then they updated it to this. Now, the interesting part is not any of those look like a ventilator. ANI, which is the American Association of something or other, put out guidelines on what a ventilator was. If you're going to build one, here's what it had to look like. Big screen, because everybody's going to be behind tarps looking through what the disease was going to do. And We are the only company in North America that was a privately funded company that designed, built, manufactured, got it certified, got our company certified to make medical devices, and then actually sold them. So the SHA has 100 of these now, and I really hope they never have to use them. If you've never been on a ventilator, you don't want to be. So why would a 53-year-old machinist, engineer, project manager want to do a PhD? Because who would buy a ventilator from a machinist? Right? Would you? Like if you were in charge of a hospital, I said, hi, I'm Jim, I'm from Saskatchewan. We built a ventilator and I did a lot of the mold making on this. Would you buy it, please? You have no credibility. The thing that made this project work really well for us is the collaboration. But that collaboration happened in a pandemic that happens once every 100 years. So we've chosen as a company to say, you know what, we're doing it backwards, but maybe it's not backwards. In Europe, you're expected to go become a tradesman before you become an engineer. The last 2 engineers I've hired, both graduates from here, one is spending the next 3 years becoming a journeyman welder, and then he's going to start working again as an engineer. So I know we're really short on time, but that's why. I'm going to be around for another hour or something if somebody wants to ask me some questions, because I know we're tight for time.
Another class professors like coming stuff, so we need to finish right now.
Okay.
Thanks so much.